So I got really excited in the last video and accidentally hit the stop button. And I left it off at the point of where we would take these 4, 8, 12, and 16% salt solutions and we start getting their measurements by hand, their density measurements by hand. So I told you that to do these densities, you will pipette these into a empty, tared container, and you will get the weight of whatever volume you decide to dispense. I also said the lab procedure probably tells you to use a graduated cylinder, and you know what it does. So do not use a graduated cylinder, please. No, no, no to the graduated cylinder at this point. That is not what we want. Again, these are for poor labs. We do not have a poor lab. We have the equipment necessary to make you a laboratory technician. So instead of a pipette, or instead of a graduated cylinder, you will use a pipette, and it's your choice on what you pick. You can do the 1 mil, you can do the 5 mil, you can do the 10 mil, you can do the 25 mil. We really don't care. You just pick a pipette, you deliver that amount into a container, and you weigh it. And you take the weight, divide it by the volume, and you will get a density value for each one of these: 4, 8, 12, and 16. Okay, so then I'm going to come over to the side and I'm going to do a chart. I'll have a 4, an 8, a 12, and a 16 with each a density measurement. So here's my percentage, and the density measurements will be here. Now I'm just going to make it easy. I'm just going to say 0.5, 1.0, 1.5, and 2.0. I now need to realize what I do with these numbers. You know, what do you want me to do with these numbers? I don't understand. Why do I do these 4, 8s, 12, and 16s? And the reason is because what we're trying to do here is set you up what we call a calibration curve. This is the first time that you have experienced the calibration curve in the program. And we want you to do this using Excel. So if you have never, ever used Excel before, you need to let us know, and we will work you through the basics of Excel on how to generate this graph. But you're going to use Excel, you are going to generate a graph that we call a calibration curve. You are going to do a linear regression line. We'll show you how to do that in Excel when that goes on. And we want you to report an R-squared value as well. Okay, so let me walk you through how to do this using Excel if you have never had it before. So what you're seeing on the screen is my version of Excel. So you go to Excel, you open up the software, whether it's at your home computer or whether it's in the ChemTech computer room, it doesn't really matter. But all Excel will look the same as the Excels before. I'm using the Excel 2013 version. This option is available to you as a student. You do get a discount on Microsoft Office. So if you need Microsoft Word, Excel, Publisher, PowerPoint, whatever the case is, you can purchase that through the college and get a discount on it. So here is the 2013 version of Excel. If you're not using the 2013 version, yours will look extremely close. The only difference is the way that these buttons will appear up here at the very top. Bottom line, Excel is just a bunch of cells. That's all that they are. That's what they call these. So this is referenced as cell A1. This is referenced as cell B1. This is referenced as cell C5. And notice it highlights it for me so I can quickly reference to that if I need to. Excel is a very powerful tool that we use, especially later in the program. So we will become very comfortable with Excel when we go through these steps and when we go through these processes. What Excel will allow me to do is any calculation that the calculator will do for me, Excel will do it as well. And it also allows me to generate these graphical representations of data that I take in a laboratory environment. So with this lab in part 3, we will be using salt solutions. And we know what those salt solutions are. We said that they were 4, 8, 12, and 16%. So the very first thing that I do is I key those concentrations into Excel in column A. So A1 is 4, A2 is 8, A3 is 12, and A4 is 16. And then we made a density measurement for each one of them. So I can go in and I can put the density measurements in. So let's say I got 0.5 for my 4%. Let's say I got 1 for my 8%, 1.5 for my 12%, and 2.0 for my 16%. I key in those numbers. If I'm kind of hesitant on what these numbers look like, well, I can put headers on them if I want. You can insert cells at any time using Excel by just clicking the row that you want to insert. So you left click it. Then you can right click on your mouse and you can go to Insert or Insert Cell depending on what version you have. When I do that, an extra row will open up for me. And then up here at the top I can kind of put concentration in percentage there so I know what that number means. And then here I can put density, or I can put D for density, and I can put a proper unit there if I want, gram per milliliter, so I understand what units are there with these numbers. See how it cuts off my unit up here at the top of the B cell, gram per mil. It kind of feeds over into the cell next door. I can expand these cells at any time. The way that I do that is I go up here between B and C, and I'm going to see an area where I get a bar with an arrow that means move it back and forth. I move it left, I can move it right. So I left click it, and I just scoot it over until I make the window as wide as what I need to. And that just opens up the cell width for me, so it includes everything that I need to include. If I don't really like the way this looks, I want something kind of pretty, I can highlight my words up here at the top and I can bold them. And when I do that, maybe that sets it apart. I can also highlight everything that I want just like in Word, and I can center it all if I want to center it. So now it all looks nice and pretty. I can give this a row header if I want. The only thing I have to do is highlight the cells. And then right here you see a box with a line on it. If I click the drop down box, it will give me some options. I can draw a line on the bottom, I can draw one on the top, I can draw one on the left, I can draw one on the right, or it gives me some different options all the way down. Well, I'm going to draw one on the bottom border just to kind of set that part off from each other. So there we go. Well, I can highlight this thing again if I want. And let's say I want a dividing line in between my two columns. Well, I can do that as well. I click the down arrow, and then what I can do is that I can go through and click top border, left border, right border, whatever I want. It doesn't matter. But I'm just going to leave that off. But you can make it as pretty as you want to make it. Okay, so there's my data. And I told you that we are going to do this thing called a calibration curve. So what that means is that this is a density associated with this, what we call standard. And this is the density of that standard. This is the density of that standard. And this is the density of that standard. And I can plot all of this on a graph. The lab will want you to do this by hand, but why? We're not that archaic. We're going to use Excel to do the graph for us. So I'm going to highlight the data. I start up here at 4 and I just highlight both rows and I drag it down and I highlight all of the numbers that I want it to make a graph with. Everything in the first column will be part of the x-axis. That means on the bottom. And everything in the second column that I highlight will be automatically put on the y-axis. And that means the vertical one, the one that goes up and down. So the way that I insert the graph is I go up here to the top and insert with Excel 2013 version. And then I will see some labels over here that will show all kinds of different charts that I can pick from. The chart that we want is always what we call scatter plot. It is a chart that will list the data points with no line drawn through them. We just want to put the data points in, and that is it. We don't want Excel or the graph to connect anything at all. So I can click the scatter point and it shows me a couple of different variations. I can put my mouse over the scatter plot without a line. I can put it here with the line connected already and the dots are shown. I can choose this one, which is just the line. None of the dots are shown on that graph. I can look at this one and see the line and the ruggedness of the line. It's not what we call a smooth fit. It's a straight line marker. And then I also have the option of showing that same thing without the dots. What we want to choose with every single time is just the dots and the dots only. That's all that we want. So I click it. So now I see this chart that's been put into Excel and it's graphed all of the data for me. So if you look at the chart, here is my 4% concentration. I go up to that dot, and that tells me that at 4% my density should be 0.5. I go to 8%, I follow up, I scroll over. At 8% my density is a 1. 12%, I go up, I scroll over. 12% density 1.5. Your numbers will be different. Your numbers will not be the same. They won't be anywhere close. But this is how you interpret the graph that you've just made. Now the next thing that we want to do is we want Excel to draw through the line on its own. We understand that we are not perfect in the lab environment. We also understand that there's going to be room for error, and our numbers will not be perfect. By forcing Excel to plot the points only, we are telling it, do not force a line through all of these points. We know that we're going to be wishy-washy in the lab. We know that we're going to make some errors. Okay, well, this worked out too perfect for me. So what I'm going to do is I'm going to reimagine this scenario. And I'm going to do something that maybe you really will see in a lab environment. And instead of a 0.5, let's say that this is a 0.4876 or 67. Instead of a 1, let's say that this is 0.9898. Instead of a 1.5, let's say that this is a 1.5964. And now instead of a 2, let's say this is a 1.9791. Now I don't get nice clean numbers. This is very common in a laboratory. You won't get nice clean numbers. Nothing will fit perfectly, ever. And now on the chart, I see some wiggle in those data points. So how do I get Excel to draw a line through most of the data points, but not through every one? Because I know not every one of these measurements are correct. I know that all of these measurements really are off. There's error associated with every one of them. So we choose scatter plot, we plot the points on the graph, and then we mouse over the graph and click one of the data points so we can highlight all of the data. So once I left click on the data point, I will then right click on top of that, and then we see an option that will say add a trend line. And a trend line will allow Excel to draw a line through your data points, and it will understand you don't have to hit every data point, but draw a line that will be close enough to hit the majority of them. So I'm going to hit add trend line. It says, what kind of trend line do you want? Most of the time by default it will be linear. So this is what you're going to see, and this is what you're going to choose almost every single time from here onto the day that you walk across that graduation stage. It will be a linear trend line for the most part. So make sure that that's clicked, and then scroll down to the bottom and you're going to see two options down here. One will say display the equation on the chart, so we want to do that. And one will say display the r squared value on the chart, and we want to do that one as well. And then when we do that, we're going to hit OK, so it will save that information. Or you hit the X button, and that will take care of it, depending on which version you have. So notice what Excel has now done. What Excel has done is it has plotted your data points. Excel understands that not all of the data points are going to be perfect. Actually, looking at this data, I can already tell that this data point right here was a little too high. So that means if you messed up in the lab, it's a very quick way to figure out which one you messed up on. So that data point was a little high, this data point was a little low, but you know, for the most part, it gives me a straight line all the way through. And I know that it's a straight line, and I know that I can feel really good about my data if I take a look at this r squared value. This r squared value right there. The closer that is to a 1.0000, the better your data is going to be. If you get an r squared of 1, that means that all your data points lined up perfectly. You did extremely well when you did the measurements. But we know that we can't be perfect most of the time, and we know that we're not going to see an r squared of 1 most of the time. So as long as we see 3 niners for the most part, we're really doing good. And in this example, I get a 0.9931. And you know, in the beginning for what we're doing, and because many of you have never been in a lab before, 2 niners are good. 0.98 would be good. That's really what we're after. So what we want to see is a really close number to 1. 0.98, 0.99, all of those are acceptable for now. We will get more stringent later on, but for now, this is completely acceptable. On top of the r squared value, it telling me how well my numbers line up, I'm going to see this y expression, and this is the equation. This is the equation of the line that is here. Okay, so what do we do with that equation? Well, in this equation, this is very important, because other than the 4, 8, 12, and 16, you will also have an unknown that I'm going to abbreviate with a UNK. And my unknown value will have a density on it. Let's say that my density is 0.75. I do that by hand just like I did all the others by hand. The unknown at 0.75, I'm going to have to figure out what this unknown percentage is, right? I know what a density of a 4% is. I know the density of 8. I know the density of 12. I know the density of 16. Can we use that information and apply that data set to an unknown salt solution and allow me to calculate a percentage here of how much this unknown salt solution really is? And the answer is yes. You do that by the graph that you just created. So this equation tells us the relationship between the percentage and the density. Some things that we want to kind of keep in mind when it comes to the percentage and to the density. In Excel, you plotted percentage on the first column, and the percentage is going here on the x-axis. For those of you who have not had math yet, well, you're going to have a chart, and this is the x-axis, and this is the y-axis. So, first column is always the x. That means the x variable in this equation relates to your percentage, because that's what you did here. The second column is always the y. And if you notice, that's where they plotted it, the y-axis, the vertical one right here. Because this is on the y-axis, The y in this equation represents that unit, and that unit is density. So in this chart, the way that I've set it up, x is my density number, x is my percentage number, and y is my density number. So how do I use that to my advantage? Well, let's remember that equation. Y equals 0.1271x. So y is equal to 0.1271x. Put a 0 there so I don't get confused. Minus 0.0079. So minus 0.0079. That is my equation. This is what we call my regression line. That is the proper term that we use for that, regression line. Okay, so what I need to do is that I have two variables here, an x and a y. Because of the way that I set it up, x is going to represent percentage and y is going to represent my density. Well, I've already said I've taken an unknown solution and I got a density measurement of it. 0.75 is what I got. Let's pretend 0.75. I need to figure out what the percentage of that salt solution is. So I took a series of standards, I plotted a line, this equation came from that line, and I need to use the equation to solve for the percent. Well, this is density. Density goes into the y value because that's the way I set it up. So I'm going to take this equation and I'm going to put my density value in for y. I'm going to set that equal to the rest of the equation, and I'm going to solve for my x variable. For those of you maybe who are rusty in math, how do I do this? Well, you need x by itself, and you need to get rid of all the neighbors first. You need to get rid of everybody else around it. So the way that we do that, we do the opposite of. So this is minus 0.0079. We need to get rid of this number, its neighbor, before we start tinkering with the house here. So the opposite of subtraction is addition. So I'm going to add 0.0079 to each side. I'll do it here, and because mathematics is all about symmetry, I do it on the other side as well. So I can bring up a calculator here if I need it. And I can take 0.75 and then I will add 0.0079 to that. And I can hit enter. And on my calculator, I will end up getting 0.7579 as an answer. Okay, so 0.7579. That's now equal to 0.1271x, right? The whole purpose of doing this addition up here is to cancel these things out. We need to isolate x by itself. Okay, so we still need to get x by itself. We look at this number and say this is 0.1271 times x, and we are going to do the opposite of. So the opposite of multiplication is division. So we will divide by 0.1271 to each side of the equation. When I do this, these cancel out. I'm left with x on this side only, which is what we want. I can then bring up my calculator again, and I can take 0.7579 and divide it by 0.1271, and I can hit enter. And this number represents the x number of the graph. It tells me 5.96. So 5.96. Well, I've got to think about what this x represents, right? I can't ever forget that. This x number is the same x that's up here in this equation, and this x represents my percentage, right? So that means that this solution with a density of 0.75 is really a 5.96% solution of salt. It allows me a way to calculate for an unknown concentration. That is the purpose of the calibration curve, right? Now, sig figs. Remember, sig figs are important. So you want to keep in mind sig figs when you report your answer. So this is how we will use Excel to generate a graph that we call a calibration curve. Use the information of the calibration curve to figure out an unknown concentration that's given to me. You will have to do this calibration curve for the salt solutions. You will run these salt solutions by hand, and you will then run these salt solutions by an instrument. So you will have to do separate calibration curves for each method. You should have a calibration curve that represents your hand numbers when you did it by hand, and you should have a calibration curve that represents the instrumentation numbers when you do it by the instrument. Okay? So, if you're part of the first group and you're responsible of doing all of this by hand, these are the steps and processes that you need to go through. The density solid, then the pycnometer method, and then the most involved part of the process will be creating a calibration curve and using that calibration curve to figure out the concentration of an unknown that we will provide you. Do not do the graph by hand like the lab instructs you to do. You use Excel to do these graphs by hand. You will always use Excel to do the graphs by hand. Up here at the chart title, you can get fancy if you want. I actually probably would tell you to do this, and you need to let me know that this is my hand measurements. So that way I know which graph goes to which method. So you can make this as pretty as you want to make it. It doesn't really matter. I don't care. The only thing I'm looking for is data and numbers. So this is the way that you will do your hand portion and your hand measurements in the lab. So I've rambled for 30 minutes, and I've probably put you to sleep with all of the math that's going to go on with this laboratory report. But hopefully you've taken away something, and that is the use of Excel, because Excel will be your friend. Excel will also be your enemy. So don't make Excel mad, because it can make a disaster in your life.